Welcome back. Have you ever looked at a function, just a string of x's and exponents, and had absolutely no idea what it actually looks like? Well, every function has a secret shape, a hidden story, and today we're going to be mathematical detectives. Using the tools of calculus, we are going to crack the case and uncover the true shape of a curve, revealing every single peak, valley, and bend along the way.
So, here's our mystery. Here's our function. Just staring at the formula, its shape isn't obvious at all, right? Does it go up? Does it go down? Does it wiggle around? Where are the interesting parts? Let's figure it out together, step by step.
Okay, our first big clue comes from the first derivative. I want you to think of it like our compass. It tells us exactly which direction the function is heading at any given point. Is it going uphill? Is it heading downhill? The first derivative has all the answers. So this is the fundamental rule for our entire investigation. The derivative, it's really just the slope of the curve. So if that derivative, f prime of x, is positive, that means the slope is positive and our graph is climbing. If it's negative, the slope's negative and our graph is falling. It's a really simple but incredibly powerful key to the first part of our puzzle.
Think about it. If a function goes from increasing to decreasing, or the other way around, it has to pass through a point where the slope is totally flat, right? Perfectly horizontal, a slope of 0. We call these moments critical points. These are the hot spots, the places where all the action happens, signaling a potential peak or a valley. Finding them is our very first mission.
All right, let's apply this to our function. We take the derivative and we get 4x cubed minus 12x squared. Now, to find those flat spots, we just set this whole thing equal to 0. After a little bit of factoring, you can see this only happens when x is 0 and when x is 3. Boom! These are our two critical points.
Now we need to check out the areas around these critical points. So as you can see, if we test any number before we get to 3, our derivative is negative. That tells us our function is decreasing. It's heading downhill, all the way up to that point. But then for any number after 3, the derivative becomes positive, so the function starts increasing. So what does that mean? The curve goes from decreasing to increasing, right at x equals 3. That has to be a valley, a local minimum. We found our first key feature.
But, just knowing the direction isn't the whole story, is it? A car can be going downhill, sure, but is it on a straight road or is it on a winding, curved one? This is where our second clue comes in, the second derivative. It tells us about the bend of the curve, a property we call concavity. And the concept here is actually really simple and intuitive. If the second derivative is positive, the graph is what we call concave up. It's shaped kind of like a cup, ready to hold water. If the second derivative is negative, the graph is concave down, more like a frown that would spill any water you put in it. Understanding this bend is absolutely crucial for getting the final shape just right. The classic y equals x cubed graph is just a perfect example of this. If you look to the left of the origin, you can see it's concave down, like that frown. Then, right at the origin, it switches, and to the right, it becomes concave up, like a cup. That exact switch point is super important.
And that special point, the spot where the bend changes direction, is called a point of inflection. Now, remember how our critical points were where the first derivative was 0. Well, these inflection points are where the second derivative is 0. So, to find them, all we got to do is take another derivative.
So, let's find the inflection points for our function. The second derivative is 12x squared minus 24x. We set that to 0, and we find our potential inflection points are at x equals 0 and x equals 2. Awesome! More key locations for our map. Okay, let's test the regions again. For any x less than 0 or greater than 2, that second derivative is positive. So the curve is concave up, like a cup. But between 0 and 2, it's negative. So in that stretch, the curve is concave down, like a frown. And because the concavity actually changes at both x equals 0 and x equals 2, we've just confirmed it. They are for sure our points of inflection.
All right, detective time is paying off. We've gathered all of our clues, we know where the function is going up and down, and we know exactly how it's bending the whole time. Now, it's time to put it all together and create a complete map of our function's shape.
This table right here, this is our master plan. It combines our two sets of clues into one detailed description. Check it out. For x less than 0, the function is decreasing and concave up. Then, between 0 and 2, it's still decreasing, but now it's concave down. From 2 to 3, it flips back to being concave up, but it's still decreasing. And finally, after x equals 3, it's both increasing and concave up. We now have a complete play-by-play for our function.
We have done all the detective work. We've got our map. The only thing left to do now is to follow it and draw the picture. It's finally time to reveal the true shape of our mystery function.
Now, before we start drawing, we need to plot our main points of interest. We just plug our key x values, that's 0, 2, and 3, back into the original function. And that gives us the exact coordinates for our inflection points and our local minimum. These are going to be the landmarks we use to build our sketch.
So the crucial first step is to start with what we know for sure. Let's just take these key points and plot them on the coordinate plane. These dots, these are going to be the guideposts for our final sketch.
And now we just connect the dots, following the instructions from our master plan. Look, the curve comes in decreasing and concave up to our first point. Then it keeps decreasing but flips to concave down. After that second inflection point, it's still decreasing but now concave up again until it finally bottoms out at our minimum. And from there, it turns and increases, staying concave up forever. The final picture, it matches our predictions perfectly.
And there you have it. We started with just this abstract formula, and using nothing but the amazing tools of calculus, we uncovered its precise visual story. The first derivative was our compass for direction, the second derivative revealed the bend, and together they gave us the complete picture. We solved the mystery. And that leaves us with a final thought. Every single function out there has its own hidden story. With these tools, you don't have to guess what a graph looks like anymore. You can be the detective, you can find the clues, and you can reveal its true shape. So, what secret shapes are you going to uncover next?